Jeff Valenti. I'm the JWST mission scientist here at Space Telescope. This is JWebbinar 44 on JWST Pure Parallel Observations. All right. So let's talk about the types of observations, prime and parallel to begin with. A prime observation obtains data with an instrument that we call the prime instrument, and that observation controls where the observatory is pointing and what the role is. And that's what most observing proposals are asking to do, is to control the observatory. There are a few different types of parallel observations where one way or another we obtain data with a different instrument, a parallel instrument. The exact field of view depends on where the prime is pointing and on the roll angle of the observatory. And sometimes observers specify the role if they need it for their science, but otherwise we let the schedulers determine the role to help balance angular momentum torques on the observatory. So there are basically three types of parallels. Coordinated parallels are the prime observer saying, I'm going to use near cam, say, or near spec. But I also want to take near cam data simultaneously because I'm going to use that data in my science case as well. So once there's a coordinated parallel, there's no opportunity for pure parallel observers to attach to that visit anymore. Pure parallel observations, which is what we're talking about now, the observer will attach exposures using a second instrument, and they'll attach it to the prime visit. This happens not at the proposal phase. It happens after the TAC is met, after the director has awarded time, and the pure parallel proposers who got time will have an opportunity, will have to attach their pure parallel visits, their observations, their exposures, those are all synonymous actually, to prime visits that were approved during the time allocation process. And finally, there are calibration parallels where we take darks or flats or something like that that don't need to be pointed observations, but we do attach them during scheduling to prime visits when there's an opportunity. So those are the three types. Just to be clear about prime and parallel instruments, this is the field of view for JWST. There's a little indicator here that shows what 1 arc minute is, and for a given observatory attitude and role, each instrument mode looks at a different part of the sky. And so when we're talking about doing pure parallel science, somebody's looking at something that they think is interesting, and we're going to be looking at an adjacent field. And so the science has to be the sort of thing where you can get interesting scientific results looking adjacent to somebody else's field. There's a bunch of prime templates. APT has this notion of templates. If you're a prime observer, you choose the instrument and then you choose the template and then you fill out other observing characteristics. There are various prime templates that can have pure parallels attached in the left column and those that cannot in the right column. And the sense of this is the ones on the right tend to be high precision observations, either coronagraphy or transiting exoplanet type observations, where people are going for super high precision, and we at this point at least don't want to risk any sort of impact on those observations by having a parallel observation. And in the left column, it's imaging, like spectroscopy, multi-object spectroscopy, slit spectroscopy, and so forth, where the precision requirements are generally not so demanding. So by default, parallels can be attached. There are only 5 templates that can be used for the pure parallel. So we were just talking about which prime templates can we attach to. Now this chart is saying what type of pure parallel observation templates can we use when we want to attach. And there's only 5. 3 of them are imaging, and 2 of them are wide field slitless spectroscopy. Yeah, we'll talk more about that. Just for context, here are usage statistics for the first 3 cycles, pure parallel usage statistics. There were no pure parallels approved in cycle 4, so this is basically everything to date. There were 7 pure parallel programs. One of them has a second program ID to continue observing. You'll see them in a moment. There are basically 3,000 hours that were allocated to those 7 + 1 pure parallel programs, and almost that many hours, 2,900 used. There were 2,000 roughly visits, pure parallel visits, that attached to 700 prime visits. And you can see the breakdown is near-cam imaging, nearest wide field slitless spectroscopy, and near-cam wide field slitless spectroscopy, fairly equally dividing the number of visits, or parallel visits. There haven't been any MIRI imaging visits yet, and nor have there been nearest imaging visits. I don't actually understand why people haven't jumped on the MIRI imaging, since JWST is so sensitive out there compared to other observatories. NIRIS, I could guess that NIRCam has a larger field of view, so people were perhaps more interested in NIRCam. 9,000 total exposures and 5 terabytes of raw data. Okay, so for reference, here are the pure parallel programs that were approved in previous cycles. The program numbers can be handy if you want to, in APT, load their program to see what it looks like, or if you want to go to the archive and see what the data looks like. So far, all but one of them have been in the field of galaxies, for example, photometric redshifts, but also strange types of galaxies and so forth. And one was a solar system program that was looking for asteroids. The fact that these are the categories in the past doesn't mean there aren't some interesting scientific cases for in other categories. In fact, I imagine there are. Okay, so let's talk a little about how one would specify a pure parallel proposal in APT. The information about pure parallels is scattered around the JDocs. There's a couple sections in the call for proposals. The methods and roadmap section of JDocs has quite a lengthy article on pure parallels. And then there are specific instructions for filling out APT, and then even more detailed instructions for the parameters that you have to fill out for pure parallels. I realize you can't click on these links during the webinar, but this will be posted as soon as possible after the webinar. Okay, so as always in APT, you in the top right corner here, I'm showing you create a new JWST proposal, and then what's always there is this opportunity to click this pure parallel box. And if you're doing a prime proposal, you just ignore that box, but we need to check that box if we're going to do pure parallels. And when you check that box, the target section that we had a moment ago goes away, because we don't get to point the observatory anymore. We're just going wherever the prime takes us. And then there's a bunch of other boxes here which will need to be filled out, and that will take quite a bit of work to get to that point. There's the total number of pointings you think you need, the minimum duration you need at each pointing, and the preferred and maximum are optional, but you can specify that as well. Fundamentally, to estimate these program level requirements, we're going to need to determine the following quantities to achieve your science goal. You need to figure out the minimum exposure duration that you need for any given exposure. ETC will be the main thing there. APT will allow you to see the allowed readout patterns and number of groups, what that exposure time, approximate exposure time that ETC says will provide you the signal to noise you need, what it would actually wind up being once you specify it in APT. You're going to need to decide how many dithers you need, and that'll be determined by the prime visit, so that will limit which prime visits you can attach to. And the minimum number of pure parallel configurations that you need per prime visit. So we're going to go into why this is an issue and how to figure that out. But it turns out that the pure parallel observations can only change configuration, like use a different filter, when the prime visit changes its configuration. So it's an important constraint. And then basically how many different regions on the sky you need to look at, which translates roughly to the number of prime visits. So if you multiply all those things together, you get how much time basically you need for science. And because it's a pure parallel program, we don't charge overhead like the prime visits for slewing and instrument configuration and so forth. There is actually some overhead, which I'll mention briefly later, but for the purposes of filling out your proposal, we're ignoring that. So you just multiply all those things together. You may have different types of observations, which need different exposure duration, different number of dither patterns or whatever. So the actual sum might be slightly more complicated than this, based per configuration, but this is the basic idea. And then as always, you click on observations and you create a new observation folder. This is a view of an APT file I created that basically has all 5 of the allowed templates that you can use when you are specifying a pure parallel observation. Any one proposal would likely just have one of these instrument template mode things. And then I'm showing, for example, you might want to observe with 3 filters with MIRI. That's going to wind up being 3 separate observations, each of which has its own exposure. You specify the filter and then also whatever you want the exposure to be. You don't get to specify the number of dithers. This is just for one exposure. For pure parallels, they're specified as an observation, which is basically a visit, which is basically a single exposure. And then you will have multiple instances of that, which you can attach. And you will attach to multiple primes to get multiple pure parallel exposures. NIRCam imaging, in this example, I have, you get 2 filters because of NIRCam has a short and a long wavelength channel. And here I'm just imagining that you wanted some line filters tuned to specific lines and then some nearby continuum. So that's 2 configurations in this hypothetical program. Nearest, just a single filter, as was done for that solar system case, for example, program. And then we have the wide field spectroscopy modes. There's 2 of them here, NIRCam and NIRIS. Here you need a direct image. As I've highlighted in the NIRIS case, we're looking at the actual on the right-hand side, the actual specification for the direct image, and then you need 1 or better 2 orthogonal dispersed configurations. When you're observing as prime, this is all managed by the template. But when you are observing as a pure parallel observer, you have to manage this yourself. You have to make sure that you have a direct image that goes with your dispersed image. And APT has in the GRISM observation section, near the bottom of the right-hand side, a way to specify which dispersed images use this particular direct image as a reference. And that information, aside from helping you keep track of things, is the only realistic way the archive can know what pieces to put together to create data products. Even if you know how to put them together, you also want other people who are getting the data from the archive to be able to know how to put them together, and ideally to have data products ready there. Some other things going on up here in the right-hand side. This is the direct image piece of the nearest wide-field slitless spectroscopy. I put the label direct image myself. I selected nearest because that's the science instrument that, in this case, I'm thinking to use for pure parallel. The target, remember the target section went away, so we can't specify target. It's just set to parallel, and there's nothing you can do about that. You do need to specify your instrument configuration and your exposure parameters. Again, you'll use ETC in the normal way to figure out what sort of what you need to put in here in order to get sufficient signal to noise to do your science. And then for the direct image, there's this association checkbox section. You will need the science duration for the math that we talked about in a slide or two ago. For this particular observation, it's always in this section here. There's also a little thing you can drag up from the bottom, and you can see the science time for everything in the folder all at once, which is convenient. And I'll just reinforce here before we go on to the next slide that when you're doing pure parallel observing, you don't just have one template that has all the pieces of your observation. You basically need to do each piece as a separate observation, and then you'll see how we make that work once you have an approved program. Okay, so I'm going to give an example here. Just that's all this hypothetical stuff that you're writing a proposal, but I think it's instructive to see what actually happens once you once we execute a pure parallel program. So I'm going to choose an example from the existing approved programs that has already executed, and we'll go through it. This was program 2211, which was the solar system one, I believe. And it's NearCam. I said it was nearest, but it's NearCam. And they've selected a couple short and a long wavelength filter here that they want, and their exposure parameters. So once you have an approved program, you will have a number of observations in your APT file that you will, so let me start here actually. Once the prime programs have all been selected and the observers have they've already submitted their APT files, a subset of all possible slots will be made available to the Pure Parallel Observer, and that will appear up here in the available parallel slot section. And then the observer will create slot groups, which are things that will go together. In this case, the prime visit is a MIRI, we'll see in a moment that it's a MIRI MRS, an IFU observation with 4 dithers. And so there will be 4 pure parallel exposures that will be put into this slot group. Those are observation 25 here. Sorry, there's 1 observation that's put in there and generates 4 pure parallel exposures. All right. So here's a piece that you don't really see in JDocs because normally it's not relevant, but I think it's helpful to understand what's going on with pure parallels. For every visit that we execute on the observatory, we upload a visit file that tells the observatory what it needs to do for that observation in that visit. And this is all the good parts that are relevant for us in 2 slides here. So there's a comment at the top that says the prime is medium resolution spectroscopy, and the parallel, which we happen to know is a pure parallel, but it could have been a coordinated parallel or a calibration parallel, is near cam imaging. There's a definition of the dither pattern at the top. It says n dithers equals 3, which actually means 3 dithers, 4 pointings, because there's the first pointing, 1 dither, second pointing, 1 dither, and so on. The visit ID of the prime is given, so that's not the one that we were looking at a moment ago in APT. This is the prime. And then there's a group which has sequences in it. And in this case, for the first group, there's only 1 sequence. Sequences are executed in parallel within a group. But this is the slew to the target and acquire a guide star part, and nothing is happening in parallel with that. So group 1, sequence 1 is get the prime on target. All right. So here comes the fun part. Group 2, the main science instrument, the prime science instrument is MIRI. Sequence 1 is the specification of the MIRI prime observation. It says we're going to use MRS and the imager. We're going to use that dither pattern that we saw above, and we're going to use the slow R1 readout pattern. There's going to be 58 groups on the short channel, 58 groups in the long channel, etc. We're going to use the subarray is going to be full. This activity statement will configure the MIRI instrument and take an exposure, dither, take another exposure, dither, take a third exposure, dither, take the 4th exposure. It's going to do all of that. The second sequence is our pure parallel observation. It's got the program and observation number of our pure parallel. So now we're back to program 2211. The science instrument is NearCam, and it's doing imaging. It's doing NERC main, and it's using all the detectors. It's got a readout pattern in a number of groups, the filter for the short, the filter for the long, pupil for the short, the pupil for the long, etc. All right. And it can't specify a different dither pattern. This is just specified consistently with the prime. And it's going to take an exposure at each of the dither positions at the same time MIRI is doing its exposures. MIRI is going to do whatever it needs to do, setting up and getting ready to take the exposure. And then when MIRI starts its exposure, the onboard scripts will start the NearCam exposure as well. This is why the system is not set up to change the configuration of the parallel instrument in the middle of the dither pattern of the prime. So this is one configuration, one prime configuration, which has 4 pure parallel slots, but all in the same configuration. You can't do 2 different filters, 2 dither positions with one filter, 2 with another. Obviously, we could have designed it all to be broken out, but there are efficiency hits if you do that. There's more overhead, or else testing all the possible combinations becomes so way more difficult, way more time-consuming and difficult. And because these scripts control what the observatory is doing, they are exhaustively tested. not just sort of tested. So bottom line, this is why the configuration of the prime dictates, each time the prime has a configuration that dictates what the parallel can do. So what does this yield? Well, if we go to MAST and we look look up the Pure Parallel program and observation ID, it says there's 4 data sets here. And if we look in detail at what they are, there's basically 40 uncalibrated detector images. The first dither location, the second dither location, the third, and the fourth. And each one of those has 10 near-cam detectors. Module A, Module B, 4 short wavelength and 1 long wavelength per module. So all of that came from that little script. And that's it. That's how pure parallels are implemented once they're approved. There's some limits on what you can do with pure parallels. I've been hinting at them. There's only 1 exposure in a pure parallel observation. The pure parallel observations are only paired with prime visits from the same observing cycle. So that's a policy statement. Primary observations have priority. If the onboard software detects that the recorder is filling up, it will automatically stop taking parallel exposures. The number of pure parallel exposures that an observer gets is not guaranteed. You have some allocation. If you remember the table I showed, you actually do wind up getting pretty much close to what you were allocated, but that's not guaranteed. It does depend on what the primes are and how operations is going. Pure parallel programs cannot include a timing constraint because you're bound by the prime, a position angle constraint because you're bound by the prime, and you can't have targets of opportunity because you're just attached to some prime and you'll go whenever that prime goes. And then new for this cycle, visits with attached pure parallels must have a data excess below 5 gigabytes. And I'm going to explain what that means in a minute. I'm going to explain now. So what is data excess? This applies to all programs, primes or pure parallels. Data excess compares the data generation rate of your exposure specification, your observation specification per visit, with the average downlink rate that we manage to get for JWST. We have 1 or 2 contacts a day. We get a certain amount of time. We can get a certain amount of data down through the deep space network. So data excess is a statistical measure of how much data is either backing up or clearing out of the recorder due to a single visit. If you have a long visit, then you can accumulate more data without sort of violating your quota. If you have a short visit, then your quota says you should only be taking a small amount of data. On the other hand, if you don't generate that much total data, then it's not a problem. And you have a short visit and you're generating data very quickly, but you only do it for 10 minutes, it's not a problem. So anyway, there's this yellow zone and orange zone and red zone, which compares the duration of your visit, including the slew, with how much data you're generating. And the farther up you go into the upper left, the more you're putting data on the recorder that's not getting downlinked and making it hard for schedulers to do their job. This was the data excess in cycles 1 to 3 for the primes before the pure parallel programs attached to the primes. Oops, wrong way, sorry. Here it is. And this is the data excess after. So you can see that one of the resources that pure parallel observations use is downlink bandwidth. This was all comfortably in the yellow, and now there are some in the orange and even the red. So in consultation with the JSTUC, we have decided that for this cycle, we're going to make a rule that if you attach a pure parallel, the visit can't be in the orange or the red zone. And you can see that there's only not that many, 20 or something pure parallel observations that cause this problem, 20 or 30 maybe. So it should still be possible to accomplish the pure parallel science goals without stressing the downlink capability. All right, just briefly on the cost of pure parallel observations. So there's some observatory costs to the hardware, basically. There are additional mechanism moves, and the mechanisms have lifetimes, and we are using up the lifetime. In some cases, we're in the single digit, 10, 15% range at worst of using mechanism lifetime. It's not infinite. There's also some additional overhead, about 40 hours per cycle, because some things actually can't be done in parallel. The script compilation for the pure parallel and the mechanism motion, and that amounts to about 40 hours per cycle. There's also the bandwidth issue, which I just explained at length. Then there's some operational costs in order to implement and maintain and improve pure parallels. We require software development and testing. There's also operations costs. The program coordinators have to handle pure parallel programs. Schedulers definitely have to do work. Data processing is automated, but there are always issues that come up that they have to debug, and certainly there have been issues with processing pure parallels. And then user support costs, and then finally there's a fixed grant pool, and so 2% of that grant pool has gone to pure parallel observers. So still, we think pure parallel has very good science potential, so that's why we have a pure parallel program. But I just wanted to take this moment to say that they're not free. There's absolutely a cost associated with them, so it's important to justify the science well.